So in the absence of coffee, it's my job to keep you awake, and let's see if I can do that. I also noticed from looking at you as an audience from here, you've got a very nice force-directed layout. You've all positioned yourselves away from everybody else, spread out nice and evenly over the room. Okay, so what's my job today? What I want to do is perhaps try and make some of the links between the theory that you've heard this morning and over the last couple of days, and some of the examples of the visual techniques that you have seen over the last couple of days, and think about how we can use our understanding of those techniques to think about design, good design, because this afternoon you're going to be designing your own visual analytics or visual approach to solving a problem. And I want to get you to think about what are the design decisions that you have to make sure that you are adequately representing the data that you're wishing to analyse in a way that's meaningful. And I'm going to do that by focusing on some visual analysis of geographic data, because I think that's a theme that is sometimes either misunderstood or overlooked when we think about the kind of design decisions that we have to make when we're constructing visual analytics systems. So I'm going to give you plenty of examples from past VASS challenges. You've had a look at a couple already, I think, and you'll certainly be looking at another one today, that we've entered in the past, as well as some other examples of software that I've developed, or the team have developed, the GI Centre, that analyse and deal with data that have a geographic component. Okay, I'm going to start with a question. And the question is, what do you think that is? I just want any ideas what it might represent. What does it remind you of? What could it be? Looks a bit like hieroglyphics. Okay, yes, it does. Hieroglyphics, collections of symbols that have some kind of meaning. Does indeed. I designed this to look a little bit like that intentionally. Anything else? What else might this be?
It's a landscape.
A landscape? Why do you say landscape? What is it that suggests landscape?
There's things that are closer here. There's a sense of distance.
Okay. Yeah, sense of distance, horizon, sort of things getting smaller as they go further away. Could be. Any other thoughts? You're seeing a pint of Guinness? Okay, all right. So you heard before about preconceptions and kind of what you bring to the interpretation of images. Yes, a bit of a kind of Rorschach test, this. Let's see if I can make this a little clearer. At some point you'll work out what this is in the next 15 seconds.
It's people moving.
It's people moving. Could be. Is it a map?
Ah, right.
It is a map. Okay, so those are all the buildings in central London. And all I've done, as you saw there, is just change their layout. Nothing else has changed. The symbolisations are identical. I'm just going to run this once more very quickly. Here, I've got all the buildings in central London ordered by size. The largest buildings at the bottom, the smallest ones at the top, which give this perspective effect. I've also orientated them so they're all facing, the long axis is facing towards the top right to give this kind of handwriting hieroglyphics effect. But I've done this to illustrate the importance of layout in design. As soon as you change the layout of things, where they appear on the page, on the screen, they carry with them different meanings. And this, the idea, although I implemented this, the idea unfortunately is not my own. It comes from an artistic piece of work from Emile Caron, who called these graphical anagrams, who took maps and changed their layout. As you can see, arranged all the parcels of land in this case rather than buildings in particular ways. So here's a map in a conventional sense on the left and in a reordered sense on the right of Berlin. Compare that with Istanbul. And what the artist, I think, was doing here was deconstructing images that appear to be familiar on the left, but also it gets you to appreciate the characteristics of the urban landscape in this case in a different way, because we get to think about the texture of the parcels of land, of the buildings, of the city, and how that might vary compared with other cities. Montpellier, south of France, characteristically different, New York, Manhattan, there. And it gets us to think about the data in a slightly different way, and possibly in a very useful way in terms of thinking about the structure of a city. But by dispensing with geography entirely and looking at the texture of the buildings that make up the city, we're looking at the same data in a different way. And I started with this because I wanted to impress upon you the value associated with layout as a design criterion. And by layout, when you've heard from Kai some issues to do with layout, all I'm talking about is the relationship between data characteristics and their positioning when visualized. And of course, you're all familiar with that as an idea through maps. And cartography and the design of maps tends to use, we're so used to using, quite a strict set of rules that say where something appears on the map is determined by where it appears in the geographical landscape that's being represented by the map. There's quite a strict relationship between those two ideas, the geography and the graphical space. And because that relationship is often quite consistent, both between maps and within any one map, we begin to learn how to interpret the graphics quite simply. And of course this has been going on for a long time, the idea that you think, well, if I've got a piece of information about this piece of geography here, and it's close to another piece of geography here, graphically I will make them close together as well. It's what makes a conventional map. This is a map of northeast Switzerland, not India as it might look from distance. But it follows this cartographic convention that you identify a layout rule that says, in this case, the geography of the data I'm interested in determines the geographic position of the graphic I'm constructing. But what I want to do, just like the graphical anagrams, is deconstruct that idea and think about when is it useful to follow that rule, the mapping between geography and graphical space, and when is it useful to perhaps change that rule, discard it. And we can apply that both to non-geographic data as much as we can to geographic data. And Kai gave you some examples of that when he was talking about graph layout, and I'll show you a few more examples today. Sorry that on this projector the details aren't too clear here, but I thought I would try and show you some examples of the VASS challenges that we've participated in the past, where we've used some of the ideas that I'm going to talk about this morning. So this was the VASS challenge from last year, where has anyone looked at this challenge? Yeah, I don't know if one of you has. A couple, yes. It got a winner from the challenge on the front row from last year as well. And so what the challenge was here was that there were a number of, imagine it was a fictitious data set, but a set of tweets, a Twitter type environment where people were tweeting all sorts of things, including whether they were feeling ill or not. And the challenge was to find out whether there was any reason for apparent outbreak of various illnesses in this fictitious place. On the right-hand side, you've got a list of tweets about all sorts of subjects. But the bit I want to bring to your attention is the top left-hand corner there, which was a conventional map which allowed us to simply symbolise whenever a tweet occurred, where it occurred in space. Now, there's absolutely nothing new to you about that idea, the idea that you use a map of something and you use the graphical position to show something about its geographical position. But I'm going to come back to this idea because I think there are ways in which we can sometimes discard that mapping between geography and graphical space in quite useful ways. I'm going to come back to this example a little later on this morning. So, I think one of the things that is helpful for you to do when you're thinking about how to design effective visual analytic tools or use them or analyse data in a graphical sense is thinking about this idea of layout and thinking, in terms of cartography at least, when is it necessary to have a precise and consistent mapping between geographic space and graphical space? In other words, when is it necessary to follow the kind of conventional cartographic rules that produces your Google Earth or your Google Maps? Sometimes it's very important, sometimes it's less so. And then thinking about that, what are the advantages in keeping those rules strict of using a conventional geographic form of layout? And what are the disadvantages? What are the consequences of doing that? Now, we're going to explore some of these ideas in the next half an hour, but has anyone got any thoughts about answers to those questions? What kinds of things might make it necessary to have this kind of conventional cartographic mapping of data? When is that useful?
I think military operation.
A military operation. What is it about a military operation that would make that important?
The targeting of knowing the terrain, the location of the targets, the precision of it.
Okay, so when you actually need to know on the ground the geography, the location of something, because you're moving troops or you're whatever you happen to be doing, where you need to find the locations of things, then having a graphical summary of those locations that is consistent is valuable. Okay. Some other thoughts?
Yeah, I guess maybe just slightly more generally. Whenever the map is providing really necessary like context or like semantic layer to the data, so whether it's like a weather map and you kind of want to know what the comments are and that kind of thing. But I guess I always think of a map as like just another data layer or a layer of context that's added to the data.
Okay, yeah, I mean, I agree. It's often used in that context. It sets the context. It's another layer and many other layers. But I think it's worth breaking down what is it about that context that's important. Sometimes, when you've got a weather map, perhaps it's absolutely vital to know where a weather front is. Maybe there are other aspects of a weather map that aren't so important. I just want to know whether I'm going to get wet today. Do I need to know precisely where that weather front is, or do I, may there be other ways of showing that? So asking the question, not just generally, have maps been used for this kind of application, but what is it about the mapping that is important here? Because if there are some things that aren't so important, as we'll see in a minute, we can use that knowledge to perhaps improve our design or give a more flexible design to the data, to the representation. There's some other suggestions at the back.
A couple of disadvantages, actually.
Yeah.
If you don't mind. One is when the distance on the map isn't really relevant to the distance that is relevant. For example, if we're planning a route and it looks close on the map, but actually have to go all the way around, then the map actually is misleading.
Okay, good.
And second is when the data is really unevenly geographically distributed. For example, if you're looking at a city and countryside and there's lots of happening and nothing in the countryside, just
Okay.
better to somehow make different geographical.
Yeah, okay, good. Two really good examples there, I think. Often what we strive for with good visual design is to use the graphical space efficiently. And as you say, if the geography determines the fact we've got some concentration down here in one city, a big gap of nothing, and then some concentration up there in the sort of left-hand corner, we're not using our graphical space very efficiently. And that's a constraint, and that may undermine the purpose of the graphic. And I think that's a useful point. And the other point about the fact that maybe it's not geographic space, distance that we're interested in, it's time, for example. When I was thinking about how to get here this morning, actually I don't care how many kilometres it is, I wanted to know what time do I need to leave the house. And on a complex journey with a bus and some walking in a tube, then space in a kind of strict geographic sense is not as important to me as the time that itself varies over space, depending on the mode of transport. Okay, any other thoughts about the... Yes?
Right, so a critical element of map is ownership. Whether you talk about national ownership, individual ownership, who owns what. There's obviously been a major criteria in developing maps.
Yeah, I think that's a really useful point as well. It's not an abstract one. It's really quite significant. If we can trace back the history of maps and map making to ownership in many ways. Military, the Ordnance Survey, interested in where ordnance is. Mapping is often about ownership of land and almost acts as a kind of legal document to say we own this land here, we're entitled to it. It had a very particular purpose. Now, there's absolutely nothing wrong with that purpose, and maps are well suited to it, but it's worth thinking about whether the purpose that you have for a particular representation of geographic data is compatible with the purpose through which maps have evolved. And sometimes if you've got a very different purpose, you may need very different designs. And so it's being aware that maps aren't some kind of objective measure of representation of geography, but they have within them a kind of history and a purpose that may not be compatible with what you're trying to do, is a useful perspective to have, because it gets you to think more widely, I think, or I'd like you to think more widely about why we need to represent data with a geographic component in a particular way. Okay, some useful points then. Let's. I'd like you to think about those when you're thinking about designs this afternoon. So let's think about this idea that we don't necessarily have to stick to this very strict mapping between geographic space and graphical space. Can we bend those rules in some useful way? Here's a familiar mapping between geographic and graphical space. So familiar that I don't even need to give it a title. You know what's being shown here. But if we change the rules, we can show different information. So I've taken that, well I haven't, in fact, Danny Dorling from Sheffield, who produced an atlas of these cartograms, as they're known, if you're not familiar with them, applied a particular algorithm that allowed you to stretch space, a graphical space, and contract graphical space according to some other item of data other than the actual geographic boundaries of the countries being shown. In this case, this is a map of population. So areas, for countries that have larger populations of people, the graphical space is expanded and contracted where there are smaller populations. An idea that's probably fairly familiar to you, but it's illustrative of this idea that we don't have to follow this strict, consistent mapping between geographic and graphical space. Here's another one. Now, what do you think, bearing in mind that we're expanding country by country according to some measure, what do you think this measure might be? GDP. Lots of hands went up, said GDP, and then they all went down again. Does everyone agree with that?
Energy consumption.
What consumption?
Energy consumption.
Energy consumption. Okay, why energy rather than GDP? What is it about? What's giving you the clue about energy consumption?
America's just so big.
Okay. So we have this idea that America is a large consumer of energy, and it's a large proportion of the map, also the large GDP. But there are some other variations. However, what about some of the Indian Ocean islands? Look at some of the Caribbean islands. It's not GDP per capita. It's not energy consumption per capita. Pollution could be. It's related to pollution.
Density of population?
It's not density of population either. Density of population in Australia is pretty small.
CO2 output?
CO2 output, yes, so we're getting there. It's actually flights per capita. And there are subtle variations here that, depending on the kinds of data, I mean, roughly speaking, many of these measures are related to some measure of development, which is why GDP came up in many people's eyes there. But there are other more subtle variations that perhaps mean that there are differences depending on what's being shown. And the reason you can do this is because you've got a model in your own mind that's something like that, with which you compare the distorted versions. And you're thinking about, well, why is that bigger than I expect? What is it that would be more associated with this particular country? What would be less associated with this country? And it can be quite effective, partly because it's challenging our familiarity with a particular worldview. And so if you want to make an impactful point with your design, then taking the familiar and changing it. Not changing it too much, you still need to have the connection. It still needs to look roughly like a world map, but it's just been distorted enough to have to allow you to make that comparison with this mental model of the world that you might have otherwise. So distorting space can be quite a powerful and useful design tool. Let me show you one example of some other work, not by me, by Pedro Miguel Cruz, who looked at movements of traffic in Lisbon during the day. So what you're seeing is a time sequence. It's 2 o'clock in the morning at the moment, 2:20, 2:30. And you're seeing a road network on the left-hand side there that is changing according to the speed of traffic along the road. And it's using this idea that, we'll come back to your idea, that actually it's the time taken to get from A to B that's often most important when you're travelling on a daily basis in an urban context, than it is the distance. And that time is affected by everybody else who's making the same journey. So think when traffic is slow, effectively the journey is as if it's a longer journey, because it takes longer. So he was playing with this idea that we can distort graphical space and the mapping to geographic space to reflect the data space, if you like, in this case, traffic congestion within an urban context. And again, I think it's playing with this idea of the familiar, but then sort of changing it slightly. So we're challenged, our preconception of a static city map is challenged there by seeing it pulsating through the day. Let me show you one more example of distorting space. I've done quite a lot of work on movement of bicycles around London, particularly bicycles using the Boris bikes, so-called, the public bike hire scheme in London, where you can pick up a bike from one of about 600 docking stations across London, cycle wherever you like, as long as you dock it at another station sometime later. This is a live map of those docking stations where the size of the rectangle is the number of bike spaces available at those stations, and the colour relates to the number of bikes actually at those stations. Now, that uses a conventional geographic mapping. The position on the screen is equivalent to its geographic position. The trouble is you get these clusters where there may be some interesting stuff going on, and you get gaps between them. It's the point you made before as well. Nothing going on here, so I'm not using my graphic space very efficiently. What I can do is move graphic space. I'm going to go backwards and forwards a few times so you get a sense of what's going on here. So I'm maintaining some of the geography, because when I'm interested in where people cycle across London, geography is still important. I still need to know whether people are coming in or out from the edges to the centre of the city, for example. I'm interested in how people relate to the Thames and to some of the parks, so I'm maintaining some of those relationships, but I'm using space, graphical space, more efficiently by filling it up effectively. What you're seeing, the symbols here, is once you've got more space, you can put stuff inside those rectangles which previously were too small. I can zoom in if I've got the mouse here. So I go to Chancery Lane here. This is a map of the number of bikes at Chancery Lane docking station over the last 24 hours. That was this time yesterday, this is this time now. So we can see change over time, and we can see change over space. And the blue line is simply the current state of the system. So I would argue that that offers greater insight into the data, because I have changed some of the rules to do with the layout there to make more space available. And you should be thinking about, when you're thinking about design and effective use of visual analytics, what is it about the graphical layout I need to preserve, and what is it that I can discard in order to free up some of my design to do something else? Okay. And a concept that underlies a lot of good layout design that Sarah Fabricant in Zurich has certainly popularised, this idea of cognitive plausibility. And in the context of geographic data and mapping, you can summarise it by saying that things that are close together graphically are assumed, we all assume it, to be closer together thematically. They're more likely to be similar to each other. They have some stronger association. And if you didn't think that was necessarily true, just read the sentence. The fact that the T and the H and the I and the N and the G are all clustered together because they represent a word. We use it all the time.
Are there lots of counterexamples to that, though? So, for example, any city, you'll have lots of the spread of affluent boroughs to non-affluent boroughs. Yeah, maybe it gets a bit greater around the periphery, but in the hearts of big cities, it's pretty random.
There are lots of counterexamples, you're absolutely right. But I would argue there are many, 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 many more examples that, if you like, it's a default. And there are often exceptions, and they're often the interesting things. If you take population of people around the world, they're not evenly distributed. There are whole wet areas that were symbolised in blue on the previous map where nobody lives at all. But you're absolutely right. There are pockets, of course there are in London, where there are contrasting neighbourhoods, even though they're adjacent. But nevertheless, it is an assumption that we're so used to making that we should think about that in our design, that people will make that assumption unless otherwise challenged, I would suggest. And this idea of cognitive plausibility means that when you're thinking about layouts, and Kai gave lots of good examples of that, those nodes in the trees that ended up being quite close together, we are more likely to say, well, there's probably something similar about them. than the ones that were far apart. Now, they may not be the case. Sometimes that isn't the case. But there is a tendency to make that assumption. And so if you have the freedom to think about where things are laid out, and you want to say these things are somehow similar to one another, take advantage of that. Well, that's the argument I'm putting here. Let me show you an example. Let's just check this works. Right, so this is one of these force-directed layouts that Kai talked about this morning. This represents, it's still moving, a set of infrastructure items, it happens to be in Rome, that relates to the telecoms network in Rome and the power network in Rome. Each item is a particular thing. This is a high voltage cabin, power cabin here, and they're coloured by their theme. This is a telecontrol something or other. I don't know enough about the infrastructure of these networks. But the point is that each symbol represents something of interest to the analysts who were interested in the dependencies between these items. And we've got some kind of force-directed layout of the kind of example that Kai talked about that tried to say things that were highly dependent on each other. If this mobile phone mast goes down, then these other things are going to be very dependent on it. We try to make those high dependencies appear close together in the layout. So we're using the kind of rules, the force-directed rules that Kai talked about, but that the forces that attract things together are determined by some other measure, in this case, software dependability, in fact, of these particular items in the network. Now that allows people to look at the reliability of the network as a whole. If one item goes down, what impact does it have on the rest of the system? If we lose water here, what impact does that have on the rest of the functioning of the building, for example? So this is a kind of conventional force-directed layout that we can kind of we can interact with. We can kind of try and move it about, see whether it readjusts itself. Because as Kai was hinting at, that actually optimising the layout so that the things that are indeed similar do end up being close together, but still sufficiently spaced out that you can see them, is a challenge, and there's not always an optimal solution. But what I wanted to illustrate here was that, let's take the lines away for a second, that's only one layout, and perhaps we're interested in the geography. This is, after all, a real city. There's no geography shown here, but I can make geography appear by just dragging the slide up here. I'm going to change the layout rules. I'm just going to say, where this appears on the graphical space is now going to start to be influenced by where it is in reality in geographic space. Not completely. I don't know if you can see this from where you're sitting, but in the bottom right-hand corner there's a slider with a D for dependency on one side and G for geography on the other. I can continuously move between a very geographic layout, and let me just slide right up to the geography here. So that's where those things actually are. When it settles down, there will be, in geographic space, as opposed to where they were before in this kind of dependency space. You'll notice one of the characteristics of these force-directed layouts is that sometimes you get these irresolvable tensions, and you get instability. I'm just going to, I can make this stable if I want to, but I wanted to illustrate that is a characteristic here. So I'm playing with layout rules, but I'm playing with them in a way that allows me to interact, to say, well, if I'm interested only in the local dependencies, perhaps I want to move things down this end, arrange them in this way, and you'll see these that structure. Sorry, let's move the mouse. You can see it up here. You may have seen before these kind of little local ring structures, very important. And I want to know, for example, whether that ring structure of high dependency between these things is maintained geographically. So let's watch what happens to those rings when I move towards a geographic view. And you can see they become more spread out. And therefore, when you've got high dependencies that have a large geographic space, if those dependencies are related to physical infrastructure like cables in the ground, and they're separated by a long distance, there's potentially a vulnerability there. Now, a few other nodes that when we move between these two spaces, move a lot. You probably see a blue circle going from the bottom left to the top right. This one, if you try and keep your eye on this one here, where the mouse is, I'm going to take the lines away actually for a second. Watch that. So, oops, no, that wasn't. That's moved too quickly. So the items that move the most are the ones where their local dependency is very different to their geographic dependency. And for analysts who are looking at the kind of resilience of this network, that kind of thing can be very important. And really, that insight is gained by playing with the rules of layout. And that's really what I wanted to demonstrate there, that those rules can be played with to useful effect. Okay, a couple more examples from some VASS challenges that we were involved with a few years ago. Again, another force-directed layout. In this case, this VASS challenge was involved identifying some industrial, or not industrial, espionage, based on looking at the contacts people had made over some social network. And what this layout did first was each one of those ellipses is a person, and they are arranged graphically using a force-directed layout depending on how many other friends in a social network they had. And it showed that they were clustered depending on the kind of, some people who had very few contacts, some had very many contacts, and they had contacts with different people in different roles in an organisation. And we could have some kind of layout that reflected that structure. But we could also, just like I did with the infrastructure, rearrange exactly those same symbols, but just show their geography, because they also had a real location. These people were located in various cities around a fictitious area. It gives a very different structure, but one where geography is important. And that was used in this VASS challenge to try and provide some insight into, identify this espionage network between fictitious countries here. So we've now embedded this back into geographic space again, and we could identify some spying activity that was going on between countries using various social network connections as a result of that. Playing with layout to do that was part of the process of understanding the structure of the network and how it arose. Okay, so let's move on to the second half and think about some other design questions. Looking back at what I've just said, a useful question to ask is how can you maximise the cognitive plausibility of your layout? In other words, when someone sees the layout of the features on your graphic, will their intuition about similarity based on graphical proximity help provide insight into the structure of the data? If it doesn't, if you've got things that are close together but have no relationship to one another, it's not necessarily wrong, but it may not be taking advantage of the cognitive plausibility that good graphic design of these kinds of data often has. And then a kind of supplementary question to this, which I'm going to show you some examples of in a second, is how can you use layout to best effect to carry information with it? Because often what we're doing with visual analytics is we've got way too much data, and we have to do something to those data to simplify them so that when we show them graphically, we've got some kind of view that is interpretable to us. And that often means discarding data, aggregating data, abstracting it, all sorts of ways of reducing the complexity of the data we're showing graphically. But one of the, I think, really powerful techniques you can use is to use layout as a way of carrying information. Because unlike symbolization, layout doesn't often so much clutter a display. If you can simply arrange the same things in a different way, they can carry meaning without making it look more complicated. I'm going to show you an example of that, a few examples of that in a minute. So thinking about this question, how can you maximize the information carrying capacity of your layout in your design, I think is quite an important way of conveying information without making a graphic too complex. I'm going to take an apparently trivial example to start with. It's a classic data set, this. 3 types of iris. They all have different morphology. They have, and in particular, the two aspects of the morphology we're going to look at are the lengths of the petals and the sepals, which are a bit blurred from here, but they're the bits in between the petals here. And in fact, the length and the widths of them can be used to distinguish these 3 species of iris. On the scatter plot on the left, I've got plotted for each of a sample of irises the sepal length from left to right and the petal length from bottom to top. And the dots are coloured according to the species. So the question is, can we use the lengths and morphology of the petals and the sepals to distinguish those 3 species? And the only reason that we are able to potentially do that is because we've got this idea in our mind that the position of the dots reflects something about the characteristic. The scatter plot, I mean, we use it so often you kind of forget that we're just simply applying a set of design rules that say this data characteristic will influence the position, the layout of this symbol on the page. And I'm comparing two variables here to do that. So that's an example of layout being used in a way that's entirely familiar to us. But we can extend that idea because we can look at those four variables, sepal length, sepal width, petal length, and petal width, and show those scatter plots, but show a whole matrix of them, so we can compare every variable with every other variable in a big grid like this. And I've simply laid out those scatter plots in a consistent manner. I'm using layout to carry extra information. So if we take the right-hand column here, for example, the horizontal axis there, in all four cases in this column, represents petal width. If we take, say, this row here, then the vertical axis represents petal length. And you can see the labels down the diagonal there. So we've got every combination of sepal width and length and petal width and length. It's no more cluttered than showing those scatter plots in any other order, but the order on the page there is providing some information. And it allows us to see which combinations of the variables, when you're comparing them pairwise, are most discriminating when we're thinking about separating the three coloured clusters. For example, let's take one that's not discriminating. That's a good. Where's the mouse gone? The purple and the orange here are all mixed up. So the sepal width against sepal length would not be a very discriminating way of distinguishing these two, the orange and the purple species of iris here, because the positions of the dots are all occupying the same place. In contrast, if you look at petal length against sepal length, the orange and the purple are more separate, and there's this kind of dividing line between the two. So I can navigate my way around that multivariate space simply by using layout here in a consistent manner. And indeed, you've already seen alternative layouts that use that show variables like this. So the parallel coordinates plot, which I think you've seen before, and certainly it was in the pre-reading for the workshop, described how these work. But really, that's just another example of applying the layout rules in a different way. Instead of taking your two axes that you're comparing your data with at right angles to one another, you take one of those axes and you make it parallel to the other. And in fact, in this case, we've got all four. Once they're parallel, we can show all four at once. And once you do that, you can't show them as dots. You have to join the axes with lines, which is what the parallel coordinates plot is. So while the plot itself may not be new to you, what I'm really trying to emphasize here is it's just another set of layout rules applied to the data that you've seen previously. Let's apply that to a more VA kind of context. Let's see if I can get this working. Where's my mouse gone? Okay, so this is some work we did for Leicestershire County Council, which uses layout in a hopefully useful way. There's something called a place survey, which happens around the UK every year, where people are asked to fill out a quite lengthy questionnaire about the quality of the services that their local government is providing, their local environment, their attitudes, etc. It's a sample. In this case, this was a sample of 8,000 questionnaires in Leicestershire region. And people were asked various questions about all sorts of aspects of their citizenship, public involvement, community, access to services. So if we look at public services, for example, they're asked a whole set of questions. The details of the questions aren't too important here, other than, I don't know if you can see, I can only just see this myself. So questions about services from the local government, rubbish, recycling, buses, sports, libraries, museums, etc. People's responses I've symbolised with a circle. Essentially, the more positive they are about a particular service, the further to the right. And we're using layout in a quite simple way, but hopefully an effective way, because I can, I hope, sort these graphs by response. So in other words, we put all of the services that people are most positive about towards the top, and they're with the circle furthest to the right, and the ones they're most negative about towards the bottom. So we're using layout there. I haven't changed the symbolisation, I've just moved the positions of those symbols to show more information, to rank them, so that I can immediately see all the services that people are less positive about down here and all the ones they're more positive about. This becomes useful when you start inquiring further. So, for example, on the right-hand side here, I've got the demographic breakdown of the people who answer the questions. So I can, by selecting, let's say, this age category, just look at the responses of the 18 to 25-year-olds, see whether that differs, and those are the smaller red circles here, from the responses of the population as a whole. Or if I look at the older population, there. And what you'll see is that the order reorders itself according to, from positive to negative, but based on the subset I've selected. And so simply the act of watching the things move, even if you can't follow precisely what's moved where, tells you how different any one group is to another. And I've done that without any extra symbolisation, simply by changing the layout rules. There's plenty more to explore there if you wanted to, but I don't want to keep you too long from the absent coffee. Let's continue. No, that's the wrong one. Sorry. Sorry about this, but I lost my display. It's a bit of a pain. Bear with me for a second. Okay. One more example from the VASS challenge 2 years ago, where we used layout. Again, this idea that positioning things can carry information. This was a challenge about spotting a global pandemic of a disease based on, again, this was on doctors' medical reports with various symptoms. And we did some modelling that said these symptoms suggest this disease is happening. But the important thing in terms of layout are these graphs on the right-hand side here. This is the number of incidences, predicted instances of a disease over time. So we've got the beginning of, I don't know, March, whatever it was, to June over time, consistently for all of these different places. So each of these graphs is a different place, but I've aligned them vertically so that I can look at how the disease has progressed over time. Particularly this vertical bar, which can be moved interactively, allows me to see whether the disease is picked up more slowly or more rapidly in particular different places at any given point in time. So again, it was an example of just using layout to convey information about the temporal passage of a disease. Okay, right, the last theme that I want to cover that relates to some of the characteristics of data that have a geographic component but can be applied more widely to all sorts of other data as well. And it relates to this idea of expectation. Someone already made the point that people are not evenly distributed about space. And so when we map things, if we take that literal mapping, those things will not be evenly distributed around the graphical page as well. But there's something more fundamental than that as well, I think, which is that if you're interested in any aspect of human behaviour and you plot graphically the incidence of that behaviour that you're interested in, it is very likely to be influenced strongly by simply the distribution of people. Not the phenomenon you're interested in, but the people who may or may not carry that phenomenon. And this is a problem that is often overlooked. I see it again and again and again, particularly in popular media. Let me show you an example. BBC were very proud to produce this interactive mapping application that allowed you to find every death on every road since 2000, I think. And you could find out, is my road a dangerous one? You could zoom into your map and find out how many road deaths there were. And you could break it down by category of vehicle involved in the accident, the nature of the accident, and etc. Because what you get is the same map you get for whether you look at crime or you look at almost any aspect of something just associated with people. You get lots of instances where lots of people live. You get a population density map of the UK. to a large extent. And I would argue that because we know this, because we know there's an uneven distribution of people, or countries around the world, or whatever it happens to be you're interested in, you often get much more benefit if you standardise with respect to that underlying unequal distribution. Now, I showed you a graphic way of standardising by the unequal distribution before. When we saw the bike stations, they were kind of spread around the screen into a grid. You kind of make things more evenly distributed. But another way of doing that is to say, well, how many road deaths would I expect in this location here, given the underlying population and density of roads at that location? Because deviation from expectation is often actually what we're interested in, not absolute numbers. And we can use that in our visual design as well. So back to VASS challenge. This is one from last year, where we were looking at tweets that may or may not give an indication of some kind of illness spreading around a place. So what I've done here is, through modelling the tweets, we've looked at done some text analysis, as you talked about in the last couple of days, I think, identified those tweets out of the millions that were produced that seem to be describing something about an illness that people may have received. So that you've got a list of these thousands of tweets that relate to some kind of symptoms of some kind. On the map on the left is the positions of all those tweets, where people were when they made those tweets. And this is exactly what you don't want to do initially, which is that doesn't tell you very much other than this is where people live. Because the cluster, mouse gone, the cluster here, these concentrations of lots of tweets to do with a particular illness, may well be simply because lots of people live there, and therefore people are tweeting there more often. So we need this idea of being able to standardise. Now, apologies for the colours here on this projector, it's not too clear, but what I've tried to do is standardise by looking at all tweets as a background population. So if you think about where everyone has tweeted, regardless of the subject, that gives you an underlying background population of where the people who are more likely to be sending messages on their phones or whatever it was to give us our information. And then I've taken as a subset of that only those that relate to this particular illnesses. And I've calculated using this chi-statistic the expected value we would get if tweets about illness were in proportion to the underlying population of all tweets. And therefore, ones that are green are greater than expected, and ones that are purple are less than expected. And I don't know how clear it is from where you're sitting, but these big purple patches here, for example, are areas of high density of twittering going on, but not much of it about this particular illness. Whereas there are some concentrated patches of green here, and in fact you may be able to see there's actually a kind of plume almost of green stuff going out here, which turned out to be related to an airborne transmission of something that was causing these symptoms. Well, that's what we hypothesised based on that distribution, which we would not have been able to pick up if we just looked at the density alone. We had to standardise that with respect to the underlying density. What's probably even less clear on this projection is that there was another completely separate high incidence, that is higher than expected incidence of tweets about this illness, green ones, along with the river. And it turned out there was a separate transmission of this disease, well, poison, in fact, in the river itself, that were people who were in close proximity to it were picking up. So expectation became critical in our visual representation and understanding of the data. So it leaves this third set of design questions that I want you to kind of think about, particularly this afternoon as well, which is, if you are going to map stuff, are you actually mapping what you think you're mapping? Because you may just be mapping where people are. If you're interested in a particular kind of behaviour from people, then make sure you are actually mapping that behaviour and not simply reflecting a more dominant heterogeneous distribution around the space you're interested in. And then it's worth thinking about, well, if you've got this idea that it's deviation from expectation that you're interested in, how best might you symbolise those variations? I use colour there, but there may be other means for doing so, to do with layout, to do with other forms of symbolisation that's relevant. So I'm going to finish off with one more example that kind of brings together some of these ideas of layout, of expectation, of cognitive plausibility. And it relates to some other work that I did a couple of years ago, last year, to do with voting behaviour. you may, if those in the UK, you may recall there was a set of local elections 2 years ago where you were asked, certainly in London, to vote for 3 candidates, up to 3 candidates. The ballot paper typically looked like this. There were 3 places available for election, and typically most of the main political parties put 3 candidates up. So you had a choice typically of 9 or 12 or sometimes 15 candidates, of which you had to make a selection of 3. And my interest in this was whether layout, and in this case I mean layout of the ballot paper, because unlike for some other colleagues in other countries, we still have this quite comparatively primitive system where you go into a polling booth with a piece of paper and a pen on a pencil on a piece of string, and you put crosses on the ballot paper vertically like this. And I was interested in whether the position on the ballot paper influenced people's voting behaviour. In other words, do people are they more inclined to vote for people near the top of the ballot paper in comparison to the bottom, regardless of political affiliation or regardless of the quality of the candidate? Was there a tendency to look at the top of a long list and think, oh, these 3? That's what I was interested in doing. So apologies for the colours here, but I'm going to use some consistent colouring to start with, which is I'm going to look at the 3 main political parties, Liberal Democrats, the Conservatives and Labour Party, and I'm interested in whether that's affecting voting behaviour. Just to give you some statistics, across London there were about 6,000 candidates, of which about 5,000 were from the 3 main parties, and in the end just under 2,000 were elected. I can tell you, to jump to the conclusions of what I found out, was there are about 20 people, elected people, in your local government who are there because they were close to the top of the list. If they weren't close to the bottom, they would not have been elected. But let me show you how I arrived at that conclusion. So this is the area of London. So the first idea was this idea that we can distort space a little bit. So I'm going to take the boroughs of London and I'm going to put them into this grid pattern again. Still got geography, we've still got the southeast down here, and we've you are here somewhere in Barnet anyway. So we've still got some of the geography here, but we've used space more efficiently so we can symbolise other things inside it. So bearing that kind of map of London in mind, let's have a look at what I found out. So here I've coloured 3 political party colours here for each of those boroughs. We've got a map of geography of London. Each borough is the same size. And what I've done is, if you remember, each party put forward 3 candidates. And for each borough, I have symbolised the number of candidates from each party that got elected. But the order, the layout here, is in the vertical order on the ballot paper. So if you take the 3 Labour candidates in Barnet, for example, the candidates that are all listed alphabetically first on the ballot paper, and it's the alphabetical order of people's names that determines that vertical order on the ballot paper, they occupy the top row of each of these squares. So the question is, does this now give us some visual indication that actually if you are listed first, you're more likely to be elected than if you were listed second or third within your party? And the graphical layout here is meant to illustrate that vertical layout on the ballot paper and give some graphical evidence that indeed that is the case. There is a tendency for this kind of slope of the here. You can see this very strongly in Islington here. If you're listed first on the ballot paper, you're more likely to be elected than if you're second, than if you're third. Even more strongly so for the Liberal Democrats. In Islington, there were no Conservatives, so there's nothing there, but we can see that effect elsewhere. Here in Ealing, for example, Conservatives had the same effect. But then there's this idea of expectation I talked about before. Maybe that's, is that what we'd expect anyway? So one way in which you can compare with expectations, not to do the statistical stuff I did before, but simply generate random orders of ballot papers. So I've done exactly the same thing, but I've just randomly ordered the people on the ballot paper to see. There's one instance of one random generation of the same data. I'm going to alternate between the random distribution and just look out for the word random there to distinguish it from the actual distribution. So we can, by comparing from one to the other, we can see whether there's some consistent pattern. Now there's partial evidence there, but not whole evidence that there's something going on with the ballot ordering. So I'm going to show you one more way in which I've reordered those same data and used this idea of expectation to understand something about the data. So I'm using the same colour scheme here, where if you imagine you've got a party, the Labour Party, they've got 3 candidates. If the people voting knew nothing about the candidates other than they wanted to vote Labour, you'd expect them to vote, each of the 3 candidates to get a third of the Labour votes in total. No reason to suspect one would get more than the other. Now, of course, some local knowledge of a candidate might mean, oh, I really like this person, I'm going to vote for them, they're popular, they're unpopular, so there'll be variation. But on the whole, our expectation would be that each party would have, between its 3 candidates, have an even distribution of votes going to that party. There might be more votes going to Labour than Conservative, but within party, it should be evenly split. So that's what I've got with this colouring here. If each candidate in each ward, in each borough, had a third of its party votes, it will be coloured in white. If it has fewer than a third of the votes, it will be purple. If it has more than a third of the votes, it will be green. And the strength of the purple and green is the strength of how much more than a third they get. And then I've ordered, and this is where layout is important, I've ordered these for the 3 main parties from top to bottom based on the vertical position on the ballot paper. And even with a slightly faint projector, I hope it's clear that there is more green towards the top here than there is at the bottom. In other words, people are getting more than a third of the votes when they're towards the top of the ballot paper compared with all the people towards the bottom of the ballot paper, the W's like me and the Z's, who are alphabetically bottom of the list. They, on the whole, tend to get fewer votes. So there's quite strong graphical evidence there that there was some bias in people's voting behaviour, and I'm using layout in combination with colour to really come to that conclusion. Final slide. We can apply the same technique back to the geography. Remember I said that London was this grid. I've kind of converted London into this grid. Each of the boroughs, we had Barnet up here somewhere, Brent, Barnet here. And I've done the same thing again. I've split it into thirds just to make it a bit clearer, because I wanted to know whether this ordering effect, this bias to do with people's tendency to choose those towards the top of the ballot paper, was itself geographically related. Were there some parts of London where that was a stronger effect than others? So we're looking at scale at layout at 2 scales here: layout on the ballot paper and then layout across London. But we're using graphical layout to show both simultaneously. And we can see some examples: Tower Hamlets, strong green at the top, purple at the bottom, whereas there are others. I can't even read the writing, which borough that is from here. Hillingdon, thank you. Actually, that's quite strong as well. Waltham Forest, not quite so strong there. Redbridge, even less so. So there's geographic variation, and what I hypothesised based on this was that actually it was particularly places where the Liberal Democrats, which were often central North London, were dominant. Liberal Democrat voters tended to be the ones who are most likely to be influenced by position on the ballot paper. And you could argue this to do with being a middle party in a range of parties on the political spectrum. For the non-UK people, Liberal Democrats are a centrist party, where people are less influenced by an ideological driver to say, well, I will always vote for the party on the left of the political spectrum or the right. And if they're less ideologically driven, possibly they're more likely to be driven by other factors such as ordering on the ballot paper. There are other interpretations as well, and there's a paper, if you're interested in this kind of thing, I could circulate to anyone. But I want to conclude, because what I wanted to show through a set of examples and raising a certain set of questions really was that, first of all, I would argue that visual analytics of geographic data is much more than conventional mapping. Okay, just because geographic data have been shown on kind of Google Maps and Google Earth and in certain ways doesn't mean that's the only way in which geographic data should be shown. By bending the rules of the mapping between geographic space and graphical space, we can often add greater insight into the data we're looking at, often at not much cognitive cost, depending on how you do it. I think you should be thinking about maximising the value attached to the layout of your data, because layout, in many cases, not always, but in many cases, is something almost you get for free as a design criterion, because unlike some use of colour or symbolisation, changing the layout of things can be done in a way that doesn't clutter or add cognitive effort in its interpretation. Sometimes it does. If you take a map, completely change it in a way that it becomes completely unfamiliar, there's a cost there. But some other cases, like the examples of those kind of histograms of the disease spread that I had aligned over time, or the Leicestershire Place survey data where we looked at the response to questionnaires that were ordered by positive to negative, simply rearranging things on the page adds information without much cognitive cost, and of course with the benefit of showing more information that may be useful to you. And then this final point that I make, it applies to all sorts of data, but it is particularly common for geographic data, which is that data that themselves have some kind of structure to them, if that aspect of the structure, where people live, in the examples I gave, is not the one you're interested in, you have to standardise that structure before you start looking at variations from it. It's often overlooked, particularly in a mapping context, because we're so used to putting people on maps using those very fixed rules. Okay, at exactly 60 minutes, according to my timer, I will stop there. Thank you.